All right, let's get right into it. In this technical deep dive, we're going to explore the complex physics and control logic behind modern common rail systems. This is really for those of you in the trenches of engine development, the ones who are grappling with the huge challenges of precision fuel delivery every single day. It all starts with this number, 2,500 bar. That's over 36,000 psi. I mean, just pause and think about that. It's an absolutely colossal pressure contained inside a fuel rail, and it's the very foundation of the efficiency and power we see in today's diesel engines.
And that pressure brings us straight to the central engineering problem, doesn't it? This isn't some calm, static hydraulic system. No way. It's a violent, incredibly dynamic environment. So the real question is, how on earth does an ECU manage to hold a stable target pressure when injectors are blasting open and shut in fractions of a millisecond? Well, that's exactly what we're here to break down. So let's get our terms straight. We're talking about pressure modulation. This is not a set-it-and-forget-it deal, not at all. It's a constantly active, dynamic, closed-loop process. The ECU is always reading sensor data and making corrections dozens of times a second to hit a constantly moving target defined by speed, load, and of course, emissions.
You know, to really appreciate today's control challenges, you have to look back at how we got here. The race for higher pressure and common rail technology has been unbelievably fast, and this timeline really shows just how steep that climb has been.
Think about this. The first production system back in 1997 topped out at 1,350 bar, which was revolutionary at the time. But in just 15 years, we nearly doubled that figure. This incredible escalation in pressure forced a parallel revolution in both the control hardware and the software logic.
And this is the hardware that made it all possible. We evolved from those early Bosch CP1 pumps to the legendary workhorse, the CP3, and now into the era of the high-pressure CP4.2 and Denso HP5 series. Each new generation of pump technology was the key that unlocked the next leap in pressure.
So, we've got the pressure. But now, how do we actually control it with any kind of precision? This brings us to the very heart of the system. The ECU's closed-loop control strategy, and the actuators it uses to make things happen.
The ECU basically has two main tools in its toolbox. First, the Inlet Metering Valve, or IMV. Think of it as the gatekeeper. It decides how much fuel even gets into the high-pressure pump. It's the efficient primary method of control. Then you have the Pressure Control Valve, or PCV. This is your fast-acting fine-tuner. It sits on the high-pressure side and can bleed off any excess pressure almost instantly. They have to work together perfectly to provide precise, two-sided control.
And here's how it all comes together in the software. The ECU looks up its target pressure from these huge 3D maps. At the exact same time, the rail pressure sensor gives it the real-time feedback, the actual pressure. The ECU calculates the difference, the error, and then a proportional integral derivative, or PID, algorithm kicks in, firing off a correction signal to the actuators. And this whole loop, it repeats every 5 to 10 milliseconds. It's a relentless, high-speed cycle of measure, calculate, and correct.
Okay, now we're getting to the really fascinating part, the hidden physics, the stuff that's happening inside the rail itself. This is a factor that's absolutely critical for injection accuracy, but it's often overlooked.
So here's the crucial point you have to wrap your head around. The rail is not a calm reservoir of fuel. Forget that idea. It's more like an acoustic battleground. Every single time an injector fires, it generates a powerful pressure wave that reverberates through the entire system.
And right here, this is the visual proof. You are looking at the direct fingerprint of a single injection event on rail pressure. See that sharp vertical drop? That's the injection. But look closely at the oscillations that come right after. That's a negative pressure wave, basically a shock wave, ripping through the fuel at nearly 1,500 meters per second.
And this is why it matters so much. As this great paper from the SAE points out, these waves can cause a serious mismatch between the amount of fuel the ECU thinks it's injecting and what actually gets into the cylinder. For today's engines using multiple, closely spaced injections, this incoherence can be a disaster for emissions and for combustion stability.
So, as engineers, what do? We turn this physics problem into a clever design solution. The physical volume of the rail itself acts as a kind of hydraulic shock absorber. Its specific length and diameter are tuned almost like a musical instrument to manage how these waves reflect. Even the engine's firing order is carefully planned to prevent these waves from crashing into each other destructively.
Now, understanding all this wave theory isn't just an academic exercise. It actually gives us some incredibly powerful, non-invasive diagnostic tools. So let's take a look at how we can analyze these pressure signals to pinpoint component faults without ever turning a wrench.
First, let's establish a healthy baseline. This is an STFT analysis. Just think of it as a way to visualize the sound of the pressure inside the rail over time. Each one of these bright vertical bands represents the pressure drop from a successful injection. Notice how they're distinct, powerful, and perfectly rhythmic? That's exactly what you want to see. Okay, now look at this. This is a faulty system. See that massive gap? Right there. An entire injection event is just gone. It's completely missing from the pressure signal. The STFT makes a fault like this stick out like a sore thumb. The rhythm is broken.
And here is the diagnostic knockout punch. On the left, we see that missing injection in the pressure signal. But look over on the right. That's the injector's electrical current. The ECU absolutely sent the command to fire. You can see the pulse, clear as day. So what does that tell us? Instantly, we know the problem isn't electrical. The ECU did its job, but it didn't happen hydraulically. This points us directly to a mechanical or hydraulic fault inside the injector itself.
Beyond these advanced signal analyses, your live data stream is your best friend. If you see your commanded versus actual pressures start to drift apart under heavy load, that's a classic sign of a worn high-pressure pump. Or if that IMV duty cycle is cranked way up over 70% just to hold idle pressure, you know the ECU is working overtime to compensate for a weak pump or a significant leak. You know, telling the difference between a failing pump and excessive injector leakback is one of the most common diagnostic headaches out there.
To wrap things up, let's look at how this precise pressure modulation has become a true cornerstone of modern emissions control, and what challenges are just around the corner as we push these pressures even higher.
See, pressure modulation isn't just for performance anymore. It is a primary emissions tool. It's a constant balancing act. We'll lower the pressure at low load to reduce peak combustion temps and cut NOx, then we crank it way up to get finer atomization and obliterate particulate matter. And DPF regeneration? The precision needed for those post-injection events is entirely dependent on stable pressure control. A failure there cascades directly into major after-treatment problems.
And that leaves us with this final thought to chew on. As we engineer systems that are knocking on the door of an incredible 3,000 bar, the energy of these internal pressure waves is going to become even more significant. So what's the solution going to be? Will we find it in clever mechanical design, smarter rail geometry and internal baffles? Or will the future be in predictive software that can anticipate and counteract these waves before they even form? That, right there, is the challenge for the next generation of powertrain engineers.